All right. Thanks everyone for coming. It's my pleasure to introduce Minh-Tâm Trinh from MIT, who will talk to us about Catalan combinatorics versus nonabelian Hodge theory.
Okay. First, I'd like to thank the organizers, especially Joshua, for inviting me to speak. It's a great pleasure and honor, and thank you all for coming. So, the title of this talk is a bit of a bait and switch because I really want to start off by talking about a conjecture which involves neither Catalan combinatorics nor nonabelian Hodge theory directly. The story starts with a complex algebraic plane curve C, on which I will fix a point P. And so such a thing, I will only care about what it looks like in the neighborhood of P. So in a conformal neighborhood of P, this curve is specified just by a single polynomial two variables. So this is given by some ring R, some C comma P, which is a quotient of the power series ring in two variables, x and y, which you just think of as coordinates on the xy plane, by some polynomial f of x comma y, such that, of course, f is a separable generically, and f of 0 comma 0 is 0. So you can, throughout the whole talk, think of something like, for example, f is y to the fourth minus x cubed, for example. So there's this very beautiful conjecture, which comes from the previous decade, which relates the algebra of C at P to the ambient topology of C in the neighborhood of P. So what do I mean by algebra?
You're assuming P is a singular point, okay?
Yeah, C is going to be a singular point so that this algebra is infinite. Yeah. So I mean a singularity of the curve gives rise to a series of so-called Hilbert schemes. And I'll say exactly what those are. So this is H sub L. Parametrizing ideals I in this ring of functions R such that the dimension of the quotient R mod I is finite and equal to L. So you have one such thing for every positive integer or non-negative integer L. So these turn out to be finite unions of projected varieties. So they're actually pretty manageable things. The word scheme is just a scare word. They're actually basically varieties. And what do I mean by topology? So this is a complex curve. So the C points of C sit inside of C squared, right? Because it's a plane curve. And of course, we know that C squared is topologically R to the fourth. So what we can do is we could intersect the set of C points with a small three-sphere that surrounds the point P. And so your picture is kind of like this. So here we are drawing a cartoon of the real points of the curve C, and maybe P is the singularity. And if you're imagining the complex analog of this picture, we take a small ball around P and we look at the boundary of that ball. And in R4, a sphere is S3. So we intersect some free sphere with the curve. And this is actually, of course, over C. So it's two real dimensions, and this is three real dimensions. So this intersection, which I'll call lambda, is a one manifold embedded in S3. So that's what we call a link or not. Okay, so now we can state the so-called Oblomkov Rasmusive Conjecture. This goes back to like roughly 2012. And in fact, Alexei Volkov gave a talk about this yesterday on a different aspect. So I will state some identity with this conjecture, and then they have to explain what the terms in the identity mean. So it looks like this. So one side has your Hilbert schemes, and the other side has something which is an invariance of this link or not after isotopy. Is that visible on the, yeah, great. So in this right-hand side, there is some prefactor, which is not really important. This exponent mu is just an integer, and it won't really matter what it is for now. But if you know about algebraic geometry of plane curves, this mu is the so-called Milnor number of the singularity. So in order to continue, I have to tell you what E of y is and what P of lambda is. So just to recap, this is an identity in two variables, Q and T. The Q variable on the left-hand side tracks the L, which tells you which Hilbert scheme you're looking at. And then this E polynomial is a polynomial of the variable T. On the right-hand side, you have something which is P of lambda, and it turns out P of lambda is going to be a series in three variables, A, Q, and T. However, we will specialize so in such a way that the A variable disappears. So I'm just writing it this way to be precise, but this will also end up being simply a series in Q and T. And the conjecture says that they match. Okay.
Can I ask real quick?
Yeah.
Yeah, I missed it. Why are you doing power series in two variables for CXY?
It would be possible to just work with it would be possible just to work with this. But I want to do power series in the sense that I only care about the formal neighborhood of the points. So I don't want to look at Hilbert schemes where the support of the subscheme can be anywhere on the curve. I want it all to be concentrated at the point. Does that answer your question?
Yeah.
Okay, so the definition of E. So this E is a so-called virtual rate polynomial. So the Rory definition is that E of T comma something is this. So in this expression, this is called the virtual rate. H superscript I sub C is compactly supported singular cohomology. If you work with a complex algebraic writing, which is quasi-projected, it is endowed with this cohomology is endowed with a wave filtration, and we take the associated weighted of that wave filtration. So I denote that with GER superscript W. Then the T variable tracks the weight gradient, and you collapse the cohomological gradient. So we simply sum over the cohomology with an alternating sum. And so the way I've written it, this is a formal series whose coefficients are vector spaces. The vector spaces are it's GER W of H. So this lives in basically vector joints. So the way you can think about this is that this is a deformation of Euler characters. So when you take t to equal 1, then this simplifies. You no longer care about the weight rating, and you're just getting alternating sum over compactly supported cohomology. And so this is the order characteristic of your underlying complex variety. So just a couple more remarks. So the simplest example is we can look at the virtual weight polynomial of projective space. Actually, let me say something slightly more general. Well, let me stick with this for now. So the virtual rate polynomial of projective n space, I think, is simply some truncation in the projective space. So in general, if a variety Z is a disjoint union of pieces that look like affine space, then this weight polynomial is basically a sum of monomials corresponding to the dimensions of those affine spaces. Where you plug in a t squared for each affine space. So another way to think about this is that it's really closely related to point counting. If you were working over a finite field instead of over the complex numbers. And so another point I want to mention. So this whole conjecture, this whole story will be simplest in the case of curves which are carved out by polynomials that basically look like this. So in the case where the curve in this story is given by f equals y to the n minus x to the d, or co-prime d n. The Hilbert schemes H sub L are all paved by affine spaces in the same way, in this kind of way. And so this remark applies to them. You can basically compute their weight polynomials very explicitly just by looking at that decomposition into affine spaces. So the next thing I have to explain is the topology side of this identity. So I think probably some of it will get cut off, but
It's fine.
it's okay.
Yeah, left-hand side's good though.
Okay. So the other side is the conjecture involves P of lambda, where lambda is some topological link associated with the singularity C comma P.
I can interrupt.
Yeah.
There's something even more interesting happens when you don't collapse the homological degree as we're doing. So you take kind of Euler characteristic, or is it really absolutely fundamental? I mean,
I think that for this conjecture, nothing more interesting happens if you keep the cohomological degree. So there's this purity conjecture that, in fact, well, it's usually stated for a different variety than these Hilbert schemes, but there's some purity conjecture that says basically all the cohomology you get is pure tape, and so nothing interesting will happen. So maybe pure tape is another statement, but nothing more interesting should happen for this conjecture if you keep the homological degree as well.
So some I and J are like the same info.
Yeah, for most of the cases you can.
Okay.
sorry, what was that?
Oh, like I and J is the same information.
They should track the same thing. So this other side involves P of lambda. It's belongs to this ring. So in variables A, choose the 1/2 and T. And it's the so-called super polynomial. of lambda. It is a upgrade or informs the so-called Polynomial PT invariance of lambda. And this implies that it also informs other non-invariants which are better known. So I'm not going to say what Polynomial PT is, but this involves keeping the A and P variables. And Polynomial further specializes to things like the Alexander polynomial or the Jones polynomial of the knot. So I'm going to try to explain very, very quickly what the super polynomial of a link is. So this should be some invariant which only depends on the link up to isotopy. And the key point to constructing it is that any link in a three-dimensional space turns out to be the so-called closure of a grade. So this is a theorem going back to Alexander. And what do I mean by the closure of a grade? You can find some n and some grade on n strands. So it's a diagram that kind of looks like a bunch of n parallel strands which are allowed to intertwine, such that a diagram for the link lambda is given by taking that grade and connecting the n inputs to the n outputs just by wrapping around like this. So this is the operation called grade closure. It turns a grade on any number of strands into a topological link represented by a diagram in the plane, but viewed as a link in three-dimensional space. So in S3 or R3. So the idea is that this invariance P of lambda is constructed from in terms of a particular choice of beta. And I should remark this beta is not unique. It's not uniquely determined by lambda. So what do you have to do to beta? So there's this beautiful idea which was put into motion by Ruquier, but I think goes that very far. Originating in brilliant works of David and Louis Michel. So there's a way to lift every grade of n strands to an object of a certain homotopy category. So I write homotopy categories with a K and bounded complexes. And this category is called SDIM, and it stands for Zergo by modules. So here, SDIM, Zergo by modules, is a subcategory of the category of C adjoin T by modules equipped to the grade, where T is basically a Cartan algebra, but for now we can just think of it as like C to the n or C to the n minus 1. So this is just a fancy way of saying this is a polynomial. So the point is that this instruction, fancy R, takes a grade and spits out some kind of complex of Zergo by modulus in such a way that composition of grades corresponds to a particular kind of tensor products or convolution products in this category. And so now P of lambda is proportional to, I use this symbol to mean proportional to, the triplet gradient dimension with variables A, Q, and C of the following thing. So you take the cohomology of a complex, we're going to apply some Tor functor term by term. So Tor, with respect to two copies of this polynomial ring, apply term by term to this complex circle by modules. So just to re-emphasize, objects of SDIM are graded by modules, and so each term of R beta is endowed with an internal gradient, and I write here. And so this corresponds to the Q variable. Tor is a gradient. This corresponds to the A variable. And finally, we take the homology of the resulting complex of modules. So that gives you a final third gradient, which roughly corresponds to T. So after normalizing this by an appropriate p-factor, you get something that miraculously is invariant of the link closure of beta, and is not only dependent on beta itself. Okay.
Is there kind of like a visual like grade closure that this Tor operation is giving you, or?
Yeah, so I can say something a bit weaker. So one feature of grade closure is that it's conjugation invariant. If you imagine composing with an alpha on the top and the bottom, an alpha and alpha inverse, those will annihilate.
Yeah.
So one feature of this crazy composition of operations is that it has to produce an monoidal trace on the category of circle by modules.
Okay.
A trace in the sense that it's conjugation invariant. Okay. So, okay, so now let me say what progress has been made towards this Oblomka-Rasmussen conjecture. So, it's a theorem of Davish-Malik in 2012 that all rest is true at the limit where t equals 1. And so this is really interesting. The proof uses the detour into the world of Polynomial geometry. So the proof uses some relation from the Hilbert schemes to moduli of so-called stable pairs on a certain Polynomial people. And then a kind of induction procedure that allows you to keep simplifying the two sides of the identity. So
How did the super polynomial side manifest?
yeah, so when t equals 1,
Yeah.
the super polynomial becomes the Humphrey polynomial,
Okay,
and there basically you use the Humphrey multiplier.
okay, and that's how you looked at it.
Yeah.
Okay,
So in Malik's paper, he has this remark saying that he's skeptical of whether the techniques he uses lift to the t level to incorporate the t variable. So there is a different limit where we know the conjecture. Yeah.
Can I ask you real quick, sorry, so P lambda is polynomial in all three variables?
Yes. Yeah. So it has A, Q, and C. And the way I've written the conjecture, I killed off the A variable. There is a version of this conjecture that has the A variable, but since it's a bit more complicated, you have to use with a certain strata inside these Hilbert schemes. I'm not going to see it here, but there is a version of all three variables.
That version is also proved by Malik.
Sorry.
That version was also proved by Malik with t equals 1 or.
Yes. So Malik's theorems is with A and Q, just not with T. There is another limit where we know the result. So by combining work of Orski, Mason, Hazarani, with work of Elias and Matt Hogenkamp, who's here today, And Untitled. Also true. In the limit where q equals 1 instead, for the curves of the form y to the n minus x to the d. So I should say here, when you have this particular polynomial, we explicitly know what this link is. So the link corresponding to the curve singularity is the so-called Minh-Tâm force link. And so the points, the tour de force is that Elias and Hogenkamp made this breakthrough on calculating the super polynomial explicitly for torus links. Melly then extended their work to torus knots. And so you basically get all possible pairs of d comma n. So the first case we've done was I think the n comma n case, the so-called full twist, and its multiples.
Sorry, I have a question.
Yeah.
Why do you think q equals 1? Is this because of limitations on the geometry side?
Yeah, limitations on the geometry side. So there's this so-called shuffle conjecture, which we talked about. And the shuffle conjecture tells you how to match the super polynomial with the q variable to some other expression that looks a lot like this side, but the q variable on that side is tracking kind of the wrong thing. So it's tracking something that I'll get to later, but for the experts, it's related to this so-called heat infiltration on the compactmention code of the curve. And the problem is that I'll get to this very soon, but it's not quite the q we want on the geometry side, to the best of my knowledge. So I explained this side of the story. So in this case, so when d and n are co-prime, it turns out that this super polynomial is basically the same as the so-called rational QT Catalan number. So what is the rational QT Catalan number? Well, it's some polynomial in variables big Q and big T, which depends on a fraction d over n, which you can think about as a two-variable definition of the following binomial expression. And so the precise definition is usually given in terms of these combinatorial objects called dichotoms, which show up everywhere, including McDonald combinatorics. Notice that if you take d to be n plus 1, then this right-hand side is just the usual nth Catalan number. So this is some kind of generalization of the Catalan numbers, where you include new variables q and t, and also you have a second integer in addition to the n. So the part that Gorski and Mason did was they mapped this QT Catalan number with an expression that looks a lot like this. So this is, I'm going to give a version that is not exactly what's in Gorski, Mason, and Mazzarani for the link case as well. So Gorski, Mason did the case where there's a co-prime, and so let me try to reword this in a nicer way. So the QT Catalan numbers are only a priori defined when d and n are co-prime. But Gorski and Mason matched it with some expression, which will then make sense for arbitrary pairs d and m. And then in the further work with Vazirani, this case turns out to be compatible with the rest of the story in the way that you expect. So I'm going to credit all three authors here. And I'm also going to write a version of this statement, which has been further digested in joint work between me and Oscar Cuban. So apologies if this is a slight inaccuracy. So instead of Hilbert schemes, you have something I want to note like a cube. That's supposed to be a fancy cube. And so for cosine, this matches with the Catalan number up to a factor. And up to replacing big Q and big T with certain specializations. And I also want some power of Q up here. So I think the power of Q is like, it's involving DFN. So this Q is Q for quote. So Q sub M parameterizes R submodules. Not of R, but of the normalization of the ring R. So this is basically a polynomial ring in one variable. Such that the dimension of the quotient is out. So at this point, we can pause and compare this to that. So these are called quote schemes. And they are not the same as Hilbert schemes. Hilbert schemes are ideals of R, and this quote scheme parameterizes submodules of the normalization R. So the differences between R and the normalization are still there. And there's this fascinating thing that happens that you don't want the T variable here. You want some combination, some monomial combination of Q and C. And so the point is that to match this side with that side is its own conjecture. And this turns out to be a conjecture of Trinh in another very processed form. Oh no, I've run out of space. Okay.
Can I ask,
Yeah.
how does R act on the CU?
So, and this is an example, in the case where R is, so we were using the example, y to the fourth minus x cubed. So here, R tilde can be rewritten as, so first R can be rewritten as C adjoin U to the fourth comma U cube. The polynomial, the subring of the polynomial ring generated by these monomials. Then R tilde is just adjoining to itself. So this is a subring. Okay. So conjecture, which I would like to attribute to Schrödinger, but I think it's been discovered by several people in different forms, is that you expect for a plane curve singularity like this one, that this series involving Hilbert schemes and this series involving quote schemes or the normalization match. And this is basically where why we lose the Q variable, as Matt was asking. So this is true that Q equals 1 has formal series.
Then E missing on the right hand.
Sorry.
Is an E missing on?
Oh, I'm sorry. Yes, there is. Thank you.
That's too much collapse.
Yeah. Yeah, so it's true that Q equals 1 has formal power series, and the reason for this is there's a so-called McDonald formula. So what goes on is that you have these Hilbert schemes, which are kind of like an analog of the symmetric powers of a curve. And so there's a kind of Apple-Jacobi relationship between these Hilbert schemes and something called the compactor Jacobian of the curve, or rather this curvature. And at the same time, you can do a similar thing on the quote scheme side. And this is my contribution with Oscar. So this is easy. This is not a deep relationship. But by basically comparing, by rewriting both sides of this identity in terms of things involving the Jacobian alone, you can match these two things when Q equals 1. But these Q variables actually turn out to correspond to different filtrations on the homology of the compactor Jacobian. One of them can be rewritten in terms of so-called Rasmusive, and the other one can be written in terms of something more elementary. But we don't know that they match in general. We can check it by hand for individual examples. So, okay. What I would like to discuss in the remainder of this talk is a new approach to the Q equals 1 limit of the ORS conjecture for this y to the n minus x to the d case, the so-called force link case, which involves a very different set of tools. So these expectations go back, in fact, to at least two of the authors of the conjecture, Oblomkov and Shende, who noticed that the two sides of the identity should be related to two sides of something called nonabelian Hodge theory. So what is nonabelian Hodge theory? So I guess in a very, very zoomed out level, Hodge theory is about the topological invariance of non-topological invariance. So what I mean is that the classical Hodge decomposition is about how one way of computing homology, the so-called default homology, which depends very explicitly on the complex analytic structure of a complex variety or Taylor manifold, can be matched up with the Betty homology, the singular homology, which you can read off only from the topological, underlying topological space of the variety. So nonabelian Hodge theory, sometimes abbreviated NAHT, is about matching, in general, different kinds of moduli spaces of principal bundles. And they roughly correspond to different ways of computing non-abelian cohomology. And so these are sometimes known as the Devolt, the Deram, and the Benny sides. So the idea is that we will be doing this non-abelian Hodge correspondence over P1 marked at 2 points, 0 and infinity. And we will try to use this in order to give a new proof of the special case of ORS. So to use this. We did. We prove. For us. That equals 1. For f equals y to the n minus x to the b. With d and n coprime. So the argument should generalize to the non-coprime case, but there's this technicality involving certain things being non-complex, which makes it more difficult. So by P1, I simply mean a Riemann sphere. And we're going to be studying various kinds of bundles with structure group SLN on P1 with decorations at P plus. So let me just state the theorems which affects the proof. The setup that I will use on the Hilbert scheme side is really close to a setup that was used in separate work by a certain 4-alpha team who just put their paper on archive recently. DBMY stands for Bezrakotnikov, Wojciech Alvarez, McGree, and Jiweyu. And so the theorem on this side is basically the Canadian series or the weight polynomials of the Hilbert series matches up with some kind of series where the Q variable tracks a so-called perverse filtration on the cohomology of a double algebra space. So I will write this new filtration as GER superscript P. And this is on the cohomology of some sort of M double.
Should A be ABJ or is it IJK?
So
Yeah, H to the K.
yeah, so the J
Oh,
index is for the perverse filtration, the associated gradient of a perverse filtration cohomology. The K is indexing cohomology.
I should be K, I think. The summation is IJ, but you probably.
Oh,
take-
I see.
Yeah.
Thank you. So on the Betty side, this will correspond to the link invariant side.
Sorry, so in what morality is this first result? So this is specifically for that purpose, the singular curve.
Yeah. So this P1 has nothing to do a priori with the curve. So this is
The end of the curve becomes the SLN.
yes.
In nonabelian Conjecture. I mean.
Yes. So this is for this particular curve where there's an N and a D.
And again, they come in because N becomes a struggle, the rank of the struggle.
Yeah.
And then D becomes 1.
So D basically becomes the whole order at infinity for some irregular sum.
Okay.
Yeah, so exactly. So I'll kind of lay this out to conclude the talk. This N becomes SL. So the other theorem is that this link to the polynomial, well, there is a version which incorporates A, but again, I just tell you the version without A. So the specialization of this links to the polynomial is matched up with the series that tells you the cohomology of the Benny moduli space equipped with its weight filtration. And on the Benny side, the weight filtration and the cohomology B really do behave differently. So they don't go in lockstep. So hopefully I've done this correctly. I probably want to shift this by Q or something. So let's say this is proportional to. So the point is that for the setup that I'm going to use, it is conjectured that this filtration, I haven't told you about that, this converse filtration matches up with the wave filtration on this other side, and here I need a q to the j over 2, not j, up to halving degree. And under a certain homeomorphism between these two moduli spaces. So M de Volt and M Betty will actually be homeomorphic. But this homeomorphism is only conjectured to take the two filtrations to each other. Since we don't have that, we don't have the GPRT, I think. Yeah. But this would be an explanation for the matching. So the expectation that something like this should happen goes back to Lonco Vincente. And my contribution is to work out, well, mainly this side. This is a preprint and archive up to something I will explain. And just working out what the spaces should be, the exact conditions you need.
Don't go some kind of space of multi-space.
These ones. So since the subject really gets very technical, what they want to do is they want to tell you two ways to describe each modular space. The first way is like the description which would occur in the literature, and the second description will be purely Greek theoretical. So they want to give you both like the description you find in the papers, and also a way to describe these things at the level of elements of groups. So throughout what follows, G is SLN, where N is the same N as in the formula for the curve. Factor G is its state algebra. Gamma is going to be a fixed element of SLN. So more precisely, put zeros along the diagonal, ones on the subdiagonal, and x to the d in the corner. So this is a elements in polynomials over the real time. So this x I'm using everywhere is going to be a coordinate on P1. So x equals 0 is the point 0. Let D be the following formal combination of points in P1. So this defines a divisor. And so now, the Volt side is stable G Higgs pairs. So bundle E together with a let's see, I write this. A phi which belongs to the twist of the adjunct bundle of E by the omega 1 to twisted by D, such that at 0 it's tangential. And at infinity, in some formal neighborhood, phi is conjugate to gamma plus 1 over x, the power series of 1 over x. Dx, and then probably need to throw in minus. So this is some terrible definition, but you can rewrite it in the following way. Let me write straight Roman letter M, the Volt, and the gigantic quotients by some large So here, and upright, the bulk is the space of triples consisting of the V0, of V1, and the G infinity in the loop group of G at X times the V algebra over the porous part times the loop group at infinity such that so add G0 inverse maximum V1 belongs to has nilpotent part plus some higher order terms. That's add G infinity inverse acting on Higgs field gives you something which belongs to this orbit space. And these groups act upon these triples by some action that basically matches coordinates with coordinates. So I don't want to spend the time to write out explicit action right now, but let me just say that one can think of these V0 and G infinity as transition functions for some bundle on P1, near to 0 and near infinity. And this P1 is the part of the Higgs field, which is on the GM in the middle. And so these conditions are saying that the structure at 0 infinity has to live with, has to have certain conditions given below. So the whole reason this gamma appears, well, a short way to say it is that the characteristic polynomial of gamma is precisely the equation of the curve. So you take the characteristic polynomial of gamma in indeterminate y, you get y to the n minus s to the.
This is kind of the straightforward thing to do if you want to like do the Birkhoff factorization. So like there's P bundles, but now you want to do the Higgs field. So
Yeah.
it's like, okay.
Yeah.
Okay.
So it's Birkhoff factorization, but just with the one more transition.
Yeah, you can't just have one group anymore.
Yeah.
Yeah. Or yeah, something like that.
Okay, so
Okay.
let me just finish with the B side. And this side is fortunate, is blessedly more elementary. So this side is so-called twisted Stokes local systems over P1 that have unipotent monogamy at 0 and irregular type at infinity with differential given by, so I'll write it this way. Add gauge G times A split. And this A split is going to be some convection written as a differential. Value equal G. So here, A split is 2 and gamma split. That's the one at the end. Gamma split is basically the diagonalized form of gamma. So if you compute the eigenvalues of this thing, and you take out the factor of x, you get something like this. And I think x to the d over n. So what one is doing here is this adjective twisted means that these are Stokes local systems which you can untwist, so to speak, by passing to some branched cover of P1, some cyclic cover. And when you pass that cyclic cover, you want the structure of the connection associated to them to take some particularly simple form, which is given basically like this, in the coordinate on the cover. And here it's untwisted in the sense that the form of the connection becomes diagonal. So finally this element G, it's an element of the real algebra over x, a variable x to the negative one over n, such that G is the element that turns gamma split into gamma. So this is also a mess, but at least at the course level, there's a much simpler description of this any modular space. So we can also rewrite it as the following space. It's a space of D tuples in D copies of base to n minus 1, such that the following equation fits. So this product is going to be some elements of the G, and we require that it is unified, where f of the vector z with n minus 1 entries is the following picture. So here z is any vector in A to n minus 1, and this spits out in elements of a SLN. So this is related to compact cluster varieties. So this the course is the course space of the study moduli space, and at the same time, it contains the so-called grade variety for a certain grade that was studied recently by a bunch of teams. So Trinh, Zaslow, Shen Wen, Anton Melik, Casals, Forsky, Simental, and probably many others. And this is related to cluster varieties in the sense that I think very recently people showed that you could put a cluster structure on this thing. So what is this grade variety? It's the closed subvariety of this MB, where this product is actually equal to the identity matrix. So this is a weaker condition, which gives you a larger variety. So this is part of a larger story. So there is a geometric incarnation of the superpolynomial, which realizes the Q and T variables of the superpolynomial of a link in terms of the weight and chronological degrees on the cohomology of a certain stack, which is associated to a grade. And so the fact that this space is somehow related to the superpolynomial for the D, n squares knot comes as a specialization of that original result. I think I'm way out of time, so I'll stop there.
Oh, yeah. Thank you, Minh-Tâm. Any questions? Or for
Yeah,
the remote?
This grade variety story, usually they don't know what to do with A a lot of times, I think. Maybe my question is, how much of this M Dolbo and like
Yeah, so
like how much of that can be enhanced to include A?
yeah, so there's a map from this space to the unit variety inside of G, which simply sends this tuple to this product, because we require that this product of matrices is unified. So U admits the so-called string resolution. So this resolution of singularities, and you can form the product products. So it turns out that the valve group Sn acts on the homology of the fibers of the string resolution, and that induces a similar story for this map. And so, in particular, the homology of M twiddle tilde is endowed with a gradient preserving action of Sn. And in particular, if you take this gradient representation and you look at the isotypic components which correspond to the so-called Cook representations, the exterior powers of the standard representation, you get the A to B. So what that means is that the homology of this thing corresponds to the trivial, the invariance under Sn of the homology of this thing, and that's like the lowest A to B. But in comparison to the grade variety corresponds to the sign.
Is the inclusion of this grade variety into what you're calling M course, is that a like multiple equivalence, or do they have the same homology?
No, you should think of it as so this grade variety is like the top A to B of the super polynomial, the highest power A, and this is the lowest power A. So they're related by a full twist. And this is explained in a separate prefix on my webpage, but not yet.
So if I understand correctly, so with the idea that we can, part of the idea was that we combine those results, and you have nonabelian Hodge theory, so that you show that the polynomial is given by that.
Yeah.
Right. But can you say something about the, the ideology? I mean, why we think that the polynomial generating function has anything to do with the quantum space, with the double quantum space, and likewise, why would we think about it has anything to do with the vector quantum space?
Yeah. That's, I should definitely have gotten to that over here. So the point is that there's something very special about this choice of a curve. So there is a certain action of C star, or rather GM, on the default moduli space, under which it contracts to a central fiber. So there's some kind of C star action which contracts and default to a central fiber, which then turns out to be the compactment Jacobian associated with this curve, or rather a rational projective curve which has this as the unique singularity. And this thing is then related to the Hilbert series by this Adel-Jacobi story, which I very briefly mentioned up there. So the idea is that this generating series involving Hilbert suites can be written in terms of the homology of a single variety called the compact Jacobi, which is basically a moduli space of generalized line models. Or more precisely, portion-free coherent sheaves numerically of rank 1 in degree 0. But this Q variable then gets sent to a certain perverse filtration on this homology, and that actually comes from the Hitching map. So this M default space is endowed with the Hitching interval system, which is proper. And then by perverse truncations, you obtain a filtration in this homology. So that's really what this so-called McDonald formula is saying. It's a generalization of the usual McDonald formula for the symmetric powers of the curve to the singular case. And it's done by several authors, including Malapune and Imburini Shende and Renema.
And this relationship, so that I don't know, so it motivates a little bit the relationship to the double space. on the relation to the maximum space. So there was this article from several years ago by Shen, Truman, and maybe the third also.
Yeah,
Where they drew a relationship, right? We forgot, but there was a relationship between some Stokesy thing and some Bray thing.
yeah, yeah, so
Sorry, I don't remember, so.
that's basically right, so they matched the Humphrey polynomial of a link with some modular space constructed from a grid. They did not have the T variable. So one of the hard part, in my work from from the last couple of years was getting the T variable. And they matched it with the modular space of Stokes local systems in the case where you have greater than 2 strands. So there's a separate paper with the 4th author, Harold Williams, where they write down a remark that as a special case, our modular space gives you the modular space of Stokes local systems when n equals 2. So I'm just pointing out that you can refine the argument to incorporate the T variable for the super polynomial and to get arbitrary rank. And I think this also answers some conjectures of the nonabelian concept about matching Chern-Simons invariants with wildcard invariants.
I have a very basic question. Is there a place where one can see examples of the E and P worked out in some very, very basic cases?
Yeah. So we could say, remember my point. So the simplest case is y squared equals x cubed. So this is a curve. So in this case, the length is a knot, and it's the 2, 3 torus knot, which is simply the trefoil. The polynomial for the trefoil in full looks something like this. So I think Matt will correct me if I get this wrong. So A so I'm missing a T somewhere, but I can figure out backwards what we can do. So the point I want to get to is actually this is in the wrong. Let me just say what the limit is for the lowest degree. So if you look at the lowest A degree of this thing, we get a series that looks like this. And if you normalize this by multiplying 2 by q, you get 1 plus u squared t squared. So after multiplying by power of q, this thing is simply the 2 variable weight polynomial for the projected line. So here, both sides end up being a Riemann sphere. Both moduli spaces end up being a Riemann sphere. So at the same time, on the other side of the conjecture, you can work out what the Hilbert schemes are. So for L equals 0, 1, 2, 3, 4, and so on, you get that HL is a points, P1, P1, and it stabilizes thereafter. So if you write out the series for this, this turns out to be something like 1 plus Q plus some series like that. And this turns out to be rational with the denominator 1 of minus Q. So If I did it correctly.
Okay, well, let's thank Minh-Tâm again. If you have more questions. Well, you'll probably have to head straight to MIT, so if you have any questions, just email them or something. All right, see you all next week.